Hi, everybody. My name's Fred Crable. I'm a Director of Software Engineering for Capital One. I'm in the Auto Finance Division, and I'm going to tell you about a project that we did we call IDEAL, an intelligent decision engine for auto lending. Don't ever call your project IDEAL. It's hard to live up to it, by the way. So we're in the Auto Finance Division of Capital One. Capital One, if you don't know, is one of the biggest banks in the nation. Our Auto Finance Division is definitely one of the biggest financial divisions that services auto loans in the nation. So I don't know how many of you have actually tried to buy a car lately, one or two. And how long have you been sitting in the finance office trying to deal with the finance guy and getting different answers from different banks and those types of things? Our motto is doing banking for good. That means we're trying to give you, the customer, the best information possible to make your decisions about your auto financing. So what we've done is we built this pipeline to process auto loans. And we try to give you this information sub-second across many different vehicles, and even the dealers give them many different options. So how does an auto loan work? Well, you go in to a dealership, you fill out some paperwork, you fill out your loan application. That loan application comes through a clearinghouse, through a set of brokers for loans to Capital One. Now, Capital One takes that loan application, goes to the credit bureaus, pulls your credit bureau, several different credit bureaus, all at one time. And so we get back just reams of data about you, all of your past credit history, all your open and closed balances, everything. So we take those and we run those through analytical models, a bunch of analytical models, and we give you a score. Just like you have a FICO score or you have any other regulatory type score, we give you a score. And then we run a bunch of rules, different rules to say, how good are you for this car and this deal? How good is this deal for you based on the car? And so we have a couple different use cases we're talking about. The first use case is basically this fast data type use case, where we need to pull in all of your credit reports from the different credit bureaus. We need to do it all at the same time. We need to get it all in memory. We need to have it all in hand so we can run these models and we can run them fast. So our analytical models are looking at everything about you, about the deal structure, about the collateral. So there's literally hundreds of variables that go in these models. Hundreds of variables and many different models. So these models, they all have to execute in order for us to get a read on you and predict your worthiness and predict how well you match with those deals. So we do this hundreds of times across different permutations of different deal structures. Deal structure being the amount of cash down you put on the car, what the sales price of that car is, the terms for the car, your 7 to 60 months type terms. So we run all of these against it, and then we try to give you the best offer. So we're looking at you and the vehicle and the dealership and trying to work to give everybody the best information possible so you guys can make the best decision. The big data type use case that's in these deals with a lot with the data that's produced by this process. There's just gobs and gobs of data. The credit report itself is, if you've ever pulled your own credit report from Experian or Equifax or TransUnion, you'll know it's tens of pages for each one of the bureaus. The application and the consumer, of course, we database that in our lake. And then all of the little intermediate decisions. We're in a highly regulated business. So the government wants to inspect how we got to that outcome. So every intermediate piece of policy, every rule that we basically check against you, all has to go in the lake and be there for the end of the year when we get audited. So all of this stuff is flowing all the time. And then, of course, all the outcomes, whether we rejected you, whether we accepted you, what the terms of the offer was. All of these things go to the lake. And we take that information, we do analysis. So we're looking at historical perspectives against how well you either chose or didn't choose to accept our offer for that loan. We're looking at maybe a future projection out, whether you're going to basically pay off that loan or not, or whether you're going to keep that loan for the duration. So that, all of these financial decisions are basically made through this data. So we retrofit these models. So we're continually testing, we're continually verifying what we see out here. And then the last is a big data case where we have basically nationwide inventory. So we work with our dealerships, we work with the dealer networks, and we have an inventory of all the cars in the nation. We know how much they're worth, what color they are, all the options, all the trims, all of those things. And we have to be able to run across these sub-second. So we're able to pull this stuff into memory. There's about 3.5 million cars in the US at any given time. And we have a product called Auto Navigator, which will allow you to actually get pre-qualified for a loan and then look through the entire inventory of the nation and see what your price is for that vehicle. Not just a range of prices, not just a guess at what it would be, but the actual price. So you can go with this app in hand, go to the bank, or go to your dealer, rather, and say, this is what I got from my bank. So how do we do this? So when we started looking at these things, we're looking at different fast data pipelines, different ways to basically orchestrate a workflow of getting things in, running models. There's various steps in here. Some run in parallel, some run in sequence. But end to end, we're doing all these things in less than 250 milliseconds. So we came up with some requirements. We didn't know what all the services we wanted to put in this pipeline were. And some of them run slow, some of them run really fast. But we wanted to be able to describe a sequence of steps, a sequence of operations to gather data, run models, and then basically do analysis of those models and rules and check rules against those models. So we basically came up with a system that has a definition of what all the components are, and basically what the sequence of instructions should be. So I'll take you through some of this, but we wrote these in actors and we developed a kind of a little pseudo workflow around how actors receive and send messages. So when we conceptualize kind of at a high level what we built, we have a system with a bunch of actors. Some of them are doing model scoring. Some of them are pulling data from various data sources. It may be credit bureaus. It may be our own internal knowledge of you as a customer from Capital One from different data sources. And these decision flows are defined externally. So we can basically piecemeal together what actor should be consuming and what an actor should be publishing as his input and output, and which models that actor should run and how that actor runs those models. We do have some bridge capability to Spark through actors. There is a streaming actor that you can use as a Spark context, or you can put it off onto a Kafka bus as well. So our testing of these things, we can run tens of thousands of these models at the same time per customer, and we can scale this out using AKKA. So AKKA gives you knobs, more or less, where you can set up groups of servers that perform certain roles. Maybe they're compute intensive. Maybe they're going out to a database or doing other long running operations. So what is an actor system? So an actor system is not a new concept. An actor system is a paradigm that's been around for a while, but AKKA implements it very well. If there's one thing I wanted you to take away from this type of lecture is we have, one or two people in our organization that actually are under the covers and doing the low-level AKKA work. The rest of us, we're concentrated on what the actor does. So we can defocus off of the data pipelines, the scale-out nature, the asynchronous things that we need to do, not worry about multi-threaded programming. We simply implement an actor that has a method that receives a message and does some work. So you can keep your engineers in that paradigm. You can keep them thinking about almost a microservice architecture, something that is, bigger than a Spark streaming type service, but smaller than a microservice. So these services, these actors, they're basically dormant until you actually go out and hit one. And they handle these messages asynchronously. So to implement an actor, it's the top box. It's really not a whole lot of code. You're basically implementing an interface from a Java toolkit from AKKA, and you implement on receive methods. It's really just that straightforward. And to access the actor, you basically get a handle to the actor system, and you call that actor. Now, there's a lot of configuration around this, of course. There's YAML files that are associated. I don't have a slide for them, but YAML files that's basically set up the size of your actor pool, which is similar to a thread pool, and give you the ability to tune different aspects or add different plugins for monitoring and measurement of the actor system. So there's two different calls. There's a tell call, and then there's an ask call. The tell uses Java futures, sits there and waits for a response. The ask call, or sorry, the opposite way around. The ask call basically sits there and blocks with Java futures and waits for the response. The tell call is just an asynchronous message, fire and forget. So any other type of protocols you want to implement on top of this, it's up to you. So if you want to have two actors that just chat back and forth all day, you can do that. Or you can build these pipelines like I'm going to show you. So when we think about what we were doing, we start out with some API or ingestion point for our application. So we want to basically give a endpoint for access to this actor system to our customers, either focused through these loan clearinghouse companies or focused through an API from our third parties or our associates. So we came up with this domain-specific language to describe how we were going to handle these messages. And what we came up with was just a simple way to say, okay, here's a set of actors that perform a large, or somewhat large set of functions. And you can have many of these different message handlers, of course, but for this simple example, basically a message handler can then have either parallel or sequential type operations. And this is all done through the semantics of the actor. And it's done, I have the next slide, through a paradigm what I call a supervisor model, where the message handler is the supervisor for all of the parallel operations that want to happen. So the supervisor actor basically gets the first message and figures out what to do with it. And basically disperses either the same message to the parallel set or transposes that message and creates a new message for that parallel set. So we implemented a service interface underneath that is basically an actor. And what it does is it would read through this domain-specific language and say, okay, when I receive a message of type, what do I have in here? Message input is the class. Go and run this bean. So everything was spring-loaded. We had a set of beans, services sitting on the side. The actor comes, gets a message. He looks, inspects his sets of rules, what to do next. And he says, oh, I got a message of type message input. I know that goes to class 1 bean. So grab him, call him, run him. Keep repeating this over and over again, either in parallel or in series. The output of one is the input to the next. We would have even kind of cascading outputs where everything you want to put into these actors need to be immutable. So don't really try to change the input and pass it on and send it on. Take a message, do something with it, create a new message, send it on. You can send on the first message that you got originally, because that's what we need to do anyway, is we got an application, then we got a credit report in hand, and now we have an application and a credit report. Go score these things. Go figure out how this person's going to do against his credit. So when you break these things down, when you have these handlers, the first thing the handler does is he spins up another handler for the group. There's these things called routers. The routers basically give you the ability to give an identifier to a set of actors. So you can even associate a UUID or something with that person for that transaction and have an actor that basically is a proxy for that person's actions. These things get deactivated after so long. You can set up a timeout for them, so they're not there forever, but they're there long enough to hold your transient state, long enough to work on it and do those things. So a group in our actor system either runs a set of sequential actions or it runs a set of parallel actions. But overall, the supervisor actor, he stays around, makes sure that those things get done. If they don't get done, if one of the actors down at the bottom in the sequential fails, he'll report back to the handler, and the handler can handle that error through an error condition. So here's a couple different examples of what you may be doing with this type of pattern. On the top, maybe I'm looking through the inventory of my nationwide inventory, 3 million cars. So my inventory supervisor, he pulls up the set of inventory for somebody's zip code, say whatever the zip code is around here, and he then segments out a group of vehicles for each one of my pricing calculators to work on. So that pricing or deal calculator is just another actor. So with this, your supervisor can basically coordinate, kick off large workloads, spin that out. I call it like a scatter-gather type thing, and then collect the responses. And if you gave him a shard ID that was associated with that person, he can sit there and hold the results, build facets for those results, give you different ways to maybe look at the inventory by color, by model, those types of things. And he can sit out there and be available for any other API or paging API to come in and grab pages of vehicles that have been priced out for that customer. The other one is a deal calculator where, like I said, we go over different terms or different amounts of cash down to come back with some different APRs, different prices for your vehicle loan. And we can do all of these things really quick, tens of microseconds through all these pipelines. And not a whole lot of computers doing this either. So the semantics of what we've done, right? All of them have this on-receive method. And all of them basically talk out to some sort of bean, and they produce some output. So the message handler basically defines his current message, whatever the class of the message is going to take, and they define the relative order of how we're going to basically sequentially go through these types of operations. We can have different sets of conditions on those outputs. So after we get done with our on receive action that the bean has handled, the bean's going to produce some set of output, some class or some structure. And we can test those, and we can have conditions. This is where the branching logic comes in. If I have basically this pre-score response, before we even get into scoring somebody, we've looked at your application and you're 14 years old. We don't give loans to 14 years old. So things like that, preconditions, so we can define any type of condition and jump to another element in our actor tree. And then we have a set of consequences. Basically, a domain-specific language for defining different types of conditions. Generally, we're very coarse here in these, but then we define a different execution element to go to. So those actors, that overarching class implementation that we have, that all our actors are subclass from, know how these conditions are formed and how to test for those conditions. And that drives the next actor in the workflow. So the on receive for the next piece of the workflow is executed, and conditionally. Generally, it goes straight A to Z, goes real fast, and everything is good, but databases go down, services go down, networks go down. This is one way to, instead of hard coding the branching logic and having every actor kind of know who his buddy is and which guy to go to next, we kind of externalize this from the conditional tests. So when you put it all together, this is one of the flows that we have. A lot of conditional branching, get in the application through your decisioning service. We do some pre-bureau validation. We want to make sure we can actually go and get your bureau records. But we may branch out, we may fork some of these things. This is a really oversimplified example, but I kind of wanted to see you guys to see how things could branch out or stop or leave off in the middle. So I wanted to give you guys some things to think about. Basically, when you have all these things going at once, there are some logging services with AKKA, but if you have thousands of these transactions going on, you really have to plan your logging strategy. These things, they run so fast, and there's so much going on at one time. If you don't have details and transactions, you will lose track of what's going on. So this is something I probably learned a little late in the game, but identify actors like people. Every actor should have some identity and some state. The state may be transient. The state may be something that you need to checkpoint and keep track of. There is a plugin called AKKA Persistence that helps you with journaling of the messages, but you still have to checkpoint your transaction even with AKKA with AKKA Persistence. So AKKA Persistence will let you replay the history of every message that came into that thing, but if you don't know where you were and which messages you've processed, then you'll be in trouble. But if you think of them more like a person or a small microservice or a piece of microservice that has state, then you'll be able to keep that thing isolated, keep it something you can test and train. Limit the granularity of these scatter-gather operations. What I mean by that, when you do what I was showing you, where you take a simple search criteria and you fan it out across many different actors, there is an overhead in transmitting all of that information and a context switch when you do those things. So even if they're on the same machine, you are context switching. You are context switching to these individual actors. So look at your speed of the operation that you're encapsulating in the actor, and try to accomplish as much in that actor as you can in the amount of clock cycles that you want to get it accomplished in. So like for us, for example, we want to get people their loan processed sub-second. So I know I have a few sets of models that I need to run. I need to make sure that the actor can run all those models in sub-second and then have overhead for all the other things in my pipeline. If I was to take and go to the nth degree and fan out every one of my models to a different actor, that adds overhead. So try to keep the actor in context, working on the thing that actor does for as long as you can. And goes without saying, make sure they have all the data that they need before they start. Some of our actors go out to the wire and they get data. That's their only job, is to get data and parse data and pull data in and get it in and validate it. If you have a very chatty actor that does work and goes out and does some more work and goes out, it just doesn't create very clean boundaries between actors in any type of situation. So you want to make sure that you're basically giving them all the input that they have, that they need on their message as much as possible. And make sure all your actions are idempotent. You want to be able to replay a message. You want to be able to redo a message. If you need to in your actor, you can checkpoint things. You can do AKKA persistence things. But for the majority of everything you want to do, you want to make sure you can replay these things. You don't want to have side effects that you can't handle in a replay situation. If you want to retry these messages, if you want to retry a whole workflow or a whole set of operations through these actors, they have to be idempotent. Take checkpoints and use AKKA persistence. So the persistence mechanism, we don't use it currently. Behind the scenes, we're using a combination of Cassandra and also streaming out data through Kafka to the lake. But this is a useful tool if you do have to have, a transaction boundary where you don't want to replay a message and have it act on that message again. Okay. I think that's it. Any questions? Thalia?
Consider Spark as an alternative?
So the question was, do we consider Spark as an alternative? So we did look at Spark as an alternative to these types of things. The reason we did not use Spark is we have to require too much data ingested in real time. So we don't have it on disk or something else prepared on disk to dredge up these and run Spark algorithms across them. Also, Spark streaming introduces another little piece of latency that we didn't want to take a hit for. So mainly we use Spark for doing data manipulation or other types of offline type of queries. Okay. Yes, sir.
Consider using Scala instead of using Java for your...
Yes. And my Scala expert at the time, I asked him, how long does it take for someone to be proficient in Scala? He told me about 6 months. My project timeline was about 6 months. So it was Java or bust. Yeah, but definitely, I mean, Scala and AKKA are native. AKKA is written in Scala. Scala is a native language for AKKA. We did have parts of the system that are written in Scala, and it works really well with Java. Calling Java from Scala or Scala from Java, both of them play pretty nice together. Yes?
So how did you choose AKKA? Were you shopping around or you just...
So we looked at a few different things, but what it come down to was we don't have any middleware here. We don't have a bunch of queues or message producers or anything else to manage besides AKKA at this point. So if we were going to add, a queue or a queuing system between these, it would have been another piece of infrastructure to manage at the same time. The other thing is we embedded the whole system inside of Docker containers. So we basically deploy a set of Docker containers. They pull up their cluster information from a registry, and they register themselves together, and there's no other middleware. There's no other bus or queue products in between these things. The other thing with AKKA is you're able to kind of build out different clusters for different use cases. If you have a database-intensive set of operations, you can have a set of computers dedicated to those types of operations. And they can form and live in the same cluster. They'll just have a different namespace for those actors. So you can build out a highly intensive compute cluster for all the model scoring, and maybe a much smaller cluster that's doing all the credit bureau reports because those are slower. So you can put your focus on the processors that you want to be fast or have better disk access or so forth. Yes?
How do you set up the AKKA cluster? Just standalone or even on top of?
So AKKA is the underpinnings of Spark, if you don't know. And basically, to set up a Spark or set up the AKKA cluster, all you need to do is point one node at another node by IP. It's a piece of YAML configuration, one line with the IP address of yourself and one other node in the cluster. So it's really, really simple. It's almost too simple. So to set up the cluster, basically, you basically create the actor system and make sure you provide that YAML file with the configuration properties that tell it what two other nodes, seed nodes, for your cluster are. So it's kind of like Cassandra in that respect. You have seed nodes, and you can go to any one of the seed nodes, and they perform a quorum.
So that cluster is dedicated for AKKA only, or you run with other clusters on top of that? Or?
No, so we embed our Docker images, and we run them in Mesosphere or ECS. But other than that, no, we dedicate those systems to running the workloads for loan origination. Yeah. Yes? So since these things, the actors themselves are relatively idempotent, they're only accepting messages through a queue and only processing the messages they receive. But we do have two different clusters and two different network regions. So we have one in the East Coast and one in the West Coast. They share a Cassandra database that is then replicated active between the two systems. So the messages that are destined for one cluster never leave the cluster and go over to the disaster recovery system. They all operate within their local cluster, but through DNS routing, we can get to both of them actively. Okay? Mm-hmm. Yes, sir?
If your business rules change, how quickly you can accommodate this change?
So the question was, if our business rules change, how quickly can we accommodate these rules? So we change models all the time, and we change. We actually have a rules engine underneath it, Drools. We're using some of the things from those, and we have the logic for what the rules are actually externalized. So when the actor system boots up, it brings in the rules, it brings in the sets of models that it needs to run. So if we want to change those, we do a rolling restart, and basically those pick up new sets of rules. So, but if you want to change the behavior, how the directed graph of actors run and chain into one another, that's the JSON configuration that I showed, that domain-specific language. You basically can swap around blocks, put in new blocks with different beans, that type of thing. Yes. Well, supposedly you're adding another module or another actor, you're going to drop that in, create a new bean for it, and then expose that as an actor and put it in the workflow. Yeah. Yes, sir?
Just follow up question about the JSON domain-specific language.
Yes.
The parser, how do you create that parser?
Just by reading JSON and iterating through JSON. JSON parsing is, I could give you code for it, but basically we're just looking through sections and then we're building object models that represent those sections of code. No, it's not Xerxes. It's just a...
You write a custom logic instead of using some generic DSL parser.
Right, it's custom logic.
Some those type of things.
Yes, it's custom DSL is what it is, yeah. Mm-hmm. I mean, you could do straight line from one actor, I know I did this, now I know which guy to call next. And you could do that, embed that type of logic in each one of the actors, but we wanted the flexibility to throw one in the middle or put two in the middle or say these three things need to run in parallel. And we didn't want to make code changes to every one of the actors that did that. We kind of have this overarching thing that runs the message to the precise actor that needs to go to next. Yes, sir?
Why is the AKKA among the other options like the other platforms?
I can't hear you.
Why is AKKA among the other options? Do you have like Golang or the other platforms?
So you're asking why AKKA instead of like Golang or some of those things? Again, it comes down to skill sets of engineers. We do have some Golang processing within Capital One as a company. The group that I managed, we didn't have anybody that knew Go. We were strictly Java engineers. It's not that you could probably do these things with Go microservices and piping between those as well. You could do these in a lot of different ways, microservice architectures and those types of things. But then you start to build out some of the things that are already in AKKA, like the registry of where actors are at, the sharding IDs for holding state, the ability to do load balancing. They have plugins for detecting the operating system load and can shift messages and make sure they pipe them over to different machines. So you do get a lot of things that maybe when you're building those things from scratch, you'd have to do yourself. Okay. Yes, sir?
Question, how AKKA, integrate or communicate with Spark?
So two different ways. Either send messages to Kafka and receive them in Spark, or there is a Spark, a AKKA streaming actor. So you can actually fire up a Spark context as an AKKA actor and have an on receive that then funnels into your micro batch for processing. So it's a different type of Spark context for Spark AKKA streaming. There's a question over here.
Share some learning or best practices around debugging and actor.
So that's the beauty of this thing is it's straight up Java. So you can run it, set breakpoints, and do everything you would with your normal multi-threaded application. It just so happens that this implements a paradigm of the actor system and handles all of the messy threading stuff. So it's no different. Fire up your debug port, set your JMX properties accordingly, and you can run single node systems, right? if you don't have to run many node clusters. So debug it first in isolation. And I have not seen any issues where different systems communicating together have problems. The message always comes in the same way. It might be serialized using Google protocol buffers if it's a remote system, but the calling semantics and the way to debug it are exactly the same as any other multi-threaded program. Okay. All right. Thank you all for coming.